Howdy, howdy, physics students. We are going to be looking at learning a few vocabulary words: amplitude, frequency, wavelength. Once we get through those, we're just going to move forward a little bit and talk about the speed of a wave, and then do a few example problems. Today's lesson should go fairly quick. So let's start with amplitude up here at the top. And to learn about amplitude, amplitude is how far the particles moved from rest. So if you remember the other day, we watched the wave go around the crowd. And when you watch the wave go around the crowd, you could have, say, an amplitude of, yay. Or you could have the amplitude of, yay. And when you get those two different things, obviously the second example I just did takes a lot more energy than the first example. So this is how far the particle moves from rest. The important part is, remember, it always returns back to its position. It's the energy that moves in a wave, not the particles. The particles moving up and down is simply the vibration. So the energy that gets carried along, though, is what we're talking about when we're talking about amplitude. The particles go back to their normal resting spot. So I happen to have this super duper wonderful little PhET simulation called a wave on a string. I maybe put my face over here for this one. I don't know, right? I don't know where to put my face, so put my face right there, I guess. So this is a PhET simulation where this is just supposed to be like a line or a tension, little beads or something on a rope. This is what we call the normal line. So when I want to say an amplitude, what I'm talking about is how far did I move it from, this is harder than it looks, the resting spot. And instead of me doing it, why not just have a machine do it for me? So I can just click the oscillate button and I can freeze it at any given moment in time. Here's the normal line. If this isn't moving, if I give it an amplitude of 0, it falls right on the normal line. And the bigger the amplitude, the further it moves away from that normal resting sign. So another way to talk about this is, what I could say is, I could say that the amplitude is the distance from here to here. And I could measure that with a ruler. If I had a ruler, I could take a ruler and I could put it on there, and I'm going to start the ruler right from the 0 line, because apparently 0 on this ruler is not the end of it. And if I put that right on there, well, that says 0.93. I suppose if I wanted to try to make it a nice number like 1, I could do that. Hit play there, and I'm just going to pause it. There we go. And you can see how nice it lines up. If I put this right on 0, I have an amplitude of 1 centimeter. And no matter what I make the amplitude, I could make the amplitude be something like 0.75, and let it run for a second so that this amplitude adjusts to 0.75. And then I can measure that by measuring from the normal line. Now, just for the record, I could measure the other way too. It should not matter. Like if I make my amplitude be 1 or something close to that again, I'm just going to go for 1 because that's just nice and easy. But I don't have to measure from the normal line up. I could measure from the normal line down. So whatever the amplitude is up here, it's going to be the same down here. So I could measure the same way here, and I can measure from 0 to the normal line. So it doesn't matter whether I'm measuring a crest or a trough. The amplitude is just simply how far it's moved from the resting spot. So in your notes, I'm just going to give you a second. You can pause the video right now. You could write that down. That way you have the definition of amplitude for your next test. When we go to do that next test, definitely something that you would want to have. Amplitude. Next thing I'm going to look at is the frequency. And for frequency, it's the number of waves in a given unit of time. Now, if you notice on that same exact thing that I just had, there was another little bar that I could control frequency with if I wanted to. So frequency, pronounced nu, it's got this little curvy V symbol. That's what the symbol for nu is. It's the number of waves per unit of time. So going back to that simulation that I just had, I'm going to turn my rulers off. I'm going to put my face back up here where it was before. And look, I had a frequency thing right here. Let's leave the amplitude at 1. I can adjust the frequency. So I'm going to count the waves that are on the screen right now. Actually, I'm going to make it be one wave. And then I'm going to count the waves that are on the screen, just so you understand how to count the wave. So this should be one wave. And I am going to stop it. I'm going to make it go forward just a little bit. There we go. So one wave looks like this. A little bit, there we go. So this is half a wave. This is one full wave. So in other words, one wave is a trough and a crest together. So one wave. So if I increase the frequency, let's go up to say 2 waves. It's just the number of waves that you see in the given unit of time. I don't know how much time this screen is supposed to represent. Let's just call it a second. So this is now a frequency of 2. And again, if I stop it and let it go forward just a hair, this is 1. This is 2. So that's a frequency of 2 waves. So there you go, frequency of 2 waves. And you can see the more frequency, sometimes people think frequency refers to, speed. If that's an optical illusion. This wave is not going any faster. There's just more of them. So because there's more of them, people sometimes think, oh my God, it's moving so fast. And it's not. So here's a really, really low frequency. If I stop this at any given point in time, what I should have on my screen here is half of a wave. So it starts here. Just a trough. That's half of a wave. So frequency, the number of waves on the screen at a given point in time. Now, frequency, you do know frequency with something else. You know frequency with sound. So this is kind of nice. Drum, I got 3 drums I can click on. And frequency is a little bit harder to talk about with light, but I'm going to do it at the end of this video. But here you can see it with these drums really nice. Look at the frequency that you get down on the screen right here. There's a lot of waves in that time frame. We're going to call the distance from here to here a time frame. And there's a lot of waves in that time frame. Whereas compared to this, low frequency, high frequency, low frequency, high frequency. I could do the same thing with a different thing. There you go, a clarinet. Let's go with pitch. High frequency, low frequency, high frequency, low frequency. I think you get the idea. I can close this guy down. I'm not going to let that play anymore. So frequency is the number of waves per unit of time. When we're talking about frequency, there's a couple little formulas that you could use. The period is equal to 1 over the frequency. So if you happen to know the frequency, well then you know the period, the time frame that it takes for it to move back and forth. So that formula can be particularly useful. We will use it in the future. Make sure you write it down. I'm going to refer to it. You do not need this formula for tonight's homework, but I will be using it in the near future, so make sure you write that one down. Here's another example. If I have frequency, it's 1 over the period. So again, make sure you write those down so that you have those. You might want to pause the video, get the definition of frequency. You don't need this code thing. That's what I used to make the little notes play when I went to that website. All right, and then the last term that we're really looking at, last like vocabulary term today, is wavelength. It's this kind of funny looking curvy Y thing, pronounced lambda, and that's the distance between 2 identical parts of a wave. So if I go back to my wave on a string, there it is. Notice there's nothing down here that says anything about wavelength. And that's because the wavelength is intimately attached to a different one, the frequency. So I'm going to turn my frequency up to about 2 again. I'm just going to leave it at about 2 because then we can talk about wavelength here. And the wavelength is just simply the distance between 2 identical parts of the wave. Two identical parts. So I'm going to pause it. I need to find one part of the wave, and when I find that, say right there at the tippy top, I can go over to another part that's identical right there at the tippy top, and I could put my rulers up there, and if I have my rulers up there, I could measure that, and right from the tippy top of this one, 0, right to the tippy top of this one is, now it doesn't have to be 2 because remember there's nothing down here that's telling me what the wavelength is. So don't say that frequency and wavelength are the same thing. They're not. I'm going to show you the relationship in just a second here, but if I measure from here to here, well, let's say it looks like it's about 3.15 if I had to estimate what I thought that was. So let me play with the frequency here for a minute to see how that changes the wavelength. I'm going to make the frequency go down. And if the frequency goes down, all I got to do is find two identical parts of the wave. And if I have two identical parts of the wave, I'm just going to measure between them. So here's one part of the wave. I'm going to put this right at the front there, right there at the 0. And the wave is going up. Now it's coming down. And now it's going back up over here. So I would want to measure to right here. Now I can't see what that is because it's behind the window. But it's probably about 7. So when there's a low frequency, the wavelength is really big. If the frequency is low, the wavelength is long. Low is long. And then if the frequency increases, so like let's say there's a frequency of 1. Okay, well now if there's a frequency of 1, I just need to find two identical parts of the wave. So there we go. In this case it's going down into a trough, back up, and then it's coming down again. Now look at, when the frequency increased, the wavelength decreased. And I'm going to do that one more time. I'm going to make the frequency go up to about 1.5. I don't really care what it is. Let's let it play for a second. And when the frequency was 1.5, so I'm just going to find two identical parts. Now in this case I can measure from crest to crest. When the frequency went up, the wavelength went down. We call that an inverse relationship in science. When one variable increases, the other variable decreases. Let's make my frequency go up to about there. We'll get that to start nice right at the 0. There's one wave. One wave is a distance of 2.8. When the frequency goes up, the wavelength goes down. Two identical parts of the wave here. There we go. This is going up, this is down, so right when the frequency is this number, when the frequency goes up, wavelength goes down. So yeah, there you go. There's these three variables. Amplitude is how high it is from the resting line. Frequency is the number of waves you can see in the unit of time. And wavelength is the distance between any two parts. You can go from crest to crest. That's what I find easiest. You could measure from trough to trough. It's also pretty easy. You could measure from, like what I was doing, where it's going up, but then you got to find another spot where it's going up again. So let's take a look at the speed of a wave. At the start of the semester we covered speed. We said speed was distance divided by time, and what I want to show you is we're still using that same formula. Speed is still distance divided by time. So what you get when you're looking at this is you have to take the wavelength times the frequency. Well, wavelength, that's a distance. But it's supposed to be distance divided by time. How do you get that? I never really talked about the units back on this previous page. Just for the record, the units, the unit for a length is going to be meters. The unit for frequency is something called hertz. A hertz is exactly the same thing as it's the number of waves per second. So a hertz is technically it's a per second. You'll see that when I do the units because it's going to come up again and again. That's why I'm doing like 3 sample problems here, because this is a hard concept. This is a hard thing for people to grasp right off the bat. But the wavelength is meters. Oops, didn't mean to put a star on the page. the wavelength is meters times the frequency, which is a /second. So meters, that means my wave speed is going to be meters per second. And that's a speed. That's a speed that you're familiar with. That's a speed that you guys know. So here's the thing. For every electromagnetic wave that we have, everyone, ever, it'll never change. It's always going to be the same number. Every electromagnetic wave has a speed of 3.0 times 10 to the 8. You do not ever have to calculate the speed of an electromagnetic wave. It doesn't matter if it's a gamma ray, X-ray, ultraviolet light. It doesn't matter if it's heat radiation, a radio wave. They all travel at the same speed. A mechanical wave, however, depends on the medium. There's some relationship. Typically, it depends on how dense the medium is. We'll talk about that in the next unit on sound. But in a medium, as long as it's in that same medium the whole time, it is going to be a constant speed. As a matter of fact, it's so constant you can look it up, what the speed of waves are in different materials, as long as it's staying in that medium. If it goes from one medium to the next, well, then the speed is going to change as it goes from one medium to the next. So the speed always does depend on the medium that it's going through. For example, this is part of your homework for tonight. I'm going to give you a chart like this, and we're looking at the speed of sound, because sound is a mechanical wave. And if you notice, the speed changes depending on what gas it's moving through. And the speed changes depending on what liquid it's moving through. And then the speed of sound changes depending on what solid it's going through. So the speed of sound isn't always going to be the same. Now, if it's air at 20 degrees Celsius, this is the speed of sound, 343 meters per second. So that's kind of how you read the chart. But and it's always going to be that. If you're talking about air at 20 degrees, it's always going to be that value. If you're talking about chloroform at 20 degrees, it's always going to be that value. So as long as you have a medium, it's always going to be the exact same number all the time. Let's do a sample problem just so you understand how this kind of works and how it all plays together, and when we go through and do it. What is the speed of a wave? So I'm looking for wave speed. That has a frequency of 10 hertz. There's that unit of hertz. Frequency of 10 hertz. And a wavelength of 2 meters. So the wavelength is 2 meters. I'm looking for wave speed. Well, I got a formula for that. The formula for wave is the wave speed is the wavelength times the frequency. So that just simply means I need to take the wavelength, 2, times the frequency, 10. And remember, instead of the unit of hertz here, a hertz is the same thing as a /second. So 2 times 10 is 20 meters per second. Meters per second. It's really hard to write with a mouse, you guys. Please forgive me. Let's look at a second problem. If I were to look at a second problem, example number 2, ignore all these things up at the top. What is the wavelength? So in this case, I don't know lambda. And I have a velocity of, so that's my speed, 330 meters per second. And a frequency of, well, there's that 20 hertz thing again. Okay? So I do know a formula. The formula that I know is that, but this formula is not in a useful form because I need to find wavelength here. And if I need to find wavelength, I got to get wavelength all by itself. So what I'm going to do to get wavelength all by itself is I'm just going to simply divide both sides here. I'm going to divide both sides of this equation by frequency. And if I divide both sides of the equation by frequency, well then what I get is frequencies will cancel out over here. And I get a formula that says wave speed over frequency equals wavelength. This is another useful formula. Kind of the second one that you might want to write down for this? We had this, right? That's what we used in the last problem, but now I just developed kind of a second formula that you might want to use. So the wave speed divided by the frequency. The wave speed divided by the frequency. So I'm going to have to take 330 divided by 20. Let me do that quick with my handy dandy calculator. 330 divided by 20 is 16.5. So I'm just going to put that right over here, 16.5. What are my units going to be? 16.5 what? Well, remember, a slash second is exactly the same thing as a hertz. So the hertz and the slash second cancel out. And that's the part that's tricky. That's the part I said it's a hard concept. You got to remember that a hertz and a slash second are just going to cancel. So my unit in this case is just meters. Just meters. Boom. So there's my final answer. Make it look a little nicer. There we go. For that particular problem. I'm just going to do one more sample problem and then kind of turn you loose on your homework for today. Here's the third sample problem. I have a speed of 200 meters per second and a wavelength of 25 meters. So this one looks like I'm trying to figure out the frequency. I still got that same formula that I started with, but in this case, in this formula, I would like to figure out what the frequency is. I don't want to know what the wave speed is. I'm more interested in finding this. So if I want to get frequency all by itself, I'm going to divide both sides by the wavelength. And when I divide both sides by the wavelength, if I do it on the right, I got to do it on the left. That wavelength is going to cancel out. So I now have a new formula that says wave speed divided by wavelength equals frequency, because these are canceled out. See, these are all canceled. That's what that means. Wave speed over wavelength equals frequency. Wave speed over wavelength equals frequency. And I can do this one in my head. I don't need my calculator to do that. That's going to work out to be 8. But the question is 8 what? 8 what? 200 divided by 20. Well, meters is going to cancel meters, which leaves me with a slash second. Please don't write slash second for your answer. Technically, it's right. Technically, 8 slash seconds is right. But we're always going to write hertz for that. So don't write the slash second for a unit. Please turn it into hertz. That's how we talk about frequency. That's the unit for frequency. That's what we do. So do it as a slash second. Turn that into hertz, and we should be good. So now you should be able to go onto your homework platform and answer these questions. I'm just going to turn this assignment 25-2 into a form that you can fill out online. Notice that there's the problems here. Set them up same way we do in class. It really, really, really will help you when you go through and do that. Okay, so set them up exactly the same way that you do it in class, and it should work out for you really well. All right.